All right, let's get started. So, how's everybody doing? Not great?
No.
Yeah?
Struggling with watching the Simon Diamond. Just getting my things up already. What can you do just enjoy?
Um, like just more broadly?
Different, like, aggregating strategies. They also talk about, like, joining strategies.
Well, we talked about the shuffle hash joins and the sort merge joins.
Okay.
Those are the join strategies that Spark uses. Are you talking about like techniques for making joins faster? Like just besides those two things that Spark has built in? Okay. Yeah, sure, we can do that. One thing that I do, especially if you're chaining multiple joins together, is, let's say you have um x dot join towards y, join with z, join with w, and so on. I came across an issue once upon a time where we had to do this massive, huge group of aggregations. We had our aggregation key had, let's see, 750 million unique values, and the aggregation states were enormous. We had to store distinct values and counts for like 20 different columns, all in the same aggregation state. So these aggregation states were massive. And so we had a bunch of separate aggregations going on because the methodology had to be a little bit different. And after the aggregations, we had to join all those results together again afterward. And what was happening is that join was just like a cascaded join of about 6 different tables being combined together because they had different columns that related to the same aggregation. And in the initial version, the code I wrote was ooming, so it was running out of memory. And I figured out what the problem was. What the problem was is I was taking the largest, which was X, and I was continuously joining it with all of the other tables sequentially. And the reason that kind of thing is a problem is every time you join a table, it will take the rows in that table and shuffle them or exchange them between machines, depending on what the join key is, right? So if the join key is a particular string, it will take all of the rows with that join key value for that string and send them all to the same machine. The problem is in the largest table, the rows were huge. Like there was a lot of columns in this largest table. Even though it had the same number of rows, it had way more columns. And so what was happening is we would initially do this exchange between the join between X and Y. And so all the rows would go from X would go to one machine, all the rows from Y would go to the same machine, and that would work. But then after that, this join produces a data frame, and the data frame is basically the X data frame and the Y data frame combined. So it's the column from X and the column from Y, and the rows from X and the rows from Y column join. So every row had all the columns from X and all of the columns from Y. So we were basically increasing the number of columns in this data frame result after every join. And what wound up happening was, so after we do this initial join between X and Y, then we would have to do the join between the result of that with Z. So then we take that combined data frame, send all of its information to the same machine, send all the information from Z to the same machine over there. So we take the largest X combined with Y and shuffle that along with Z to join those. And then X, Y, and Z are all combined now in the same data frame. So now we have all the columns from X, Y, and Z in the same row. And then we have to shuffle that again and join it with W. So what's happening was we were taking the largest data frame and we were doing like 4 shuffles on it. And the problem is that Spark's memory manager isn't actually that efficient. And so because we were shuffling it multiple times, like that creates copies of the data when you shuffle it. Because when stuff is sent over the network in Spark, you have to make sure it reaches its destination before you remove it from your own memory. So shuffling it creates copies of the data. So what I did to fix this problem is I literally just changed the order of the join from the smallest first all the way down. So if you change the order of the join to be the smallest first in this chain, then you're shuffling the first item in this chain multiple times, but if it's the smallest item, that doesn't matter as much. So if let's say Z is the smallest, so we can say Z dot join, and then maybe Y is the next smallest, and then join W is the next smallest, and then after everything else, then we join X. So doing this simple switch of the order that I joined these tables in fixed the out of memory issue. just because in the top example, we were shuffling the largest data set like 6 times, and the bottom example, we're shuffling it once. So we only copied it 1 time. And I figured the Spark memory manager was not cleaning up its resources properly between stages because every single join is a separate stage.
Okay. Is it also really more different than selecting out in between like so like 1 and 2 and then all of them? That would be something that kind of shuffle the actually one.
Well, Spark should optimize those out. I say should, but I don't, I don't trust it. But it should optimize those out. Let's say you have like a column from Y, but you're filtering it out after everything is said and done. It just shouldn't include those in the first place in the initial join when it's sending stuff over the network. Yeah.
That's like asking joins, like you join in just.
You can, that depends. So what I did in my solution is I kind of I did combine everything into a single join. My solution is literally one chained expression. That's all it is. And in order to make it more efficient, I did not persist the initial reads from S3 in the same way that we do in class. So um these reads up here. So we read the stuff from Parquet, and then we just cache the stuff from Parquet in S3 in memory after we do the initial read. So here, the read is eager, right? We're loading it into memory before we actually need it. We're forcing Spark to do that. But what I do in my solution is if you just read the Parquet without doing the save, so like without doing this count business or the persistence, then it'll just read it from S3 as needed. And since my solution only uses, especially the largest table, like the page links table, it only uses the page links table in one join. And because it does that, we can stream in the page table from S3 at the same time that we're doing the join. And that saves a lot of time because that means that while you're streaming something in from S3, you can also, during the stream, do the shuffle and send rows out to other machines as the rows are coming in from S3. So everything's very pipelined when you do it that way. Does that make sense? So in my solution, it'll take the page links table, read it in from S3, and at the same time, while it's taking stuff in from S3, it'll also be doing the shuffle simultaneously. And because of that, it doesn't need to hold its own copy of the data in its memory because we haven't cached it at all. And so that makes it use less memory, and it also makes it much faster because the persistence, as you'll notice, uses memory and disk. And so if something doesn't fit in memory, it's going to spill it to disk again. And so if you do a save, if you save it and cache this, page links data frame, and then, you need to read it again in order to join on it, then it would have to read from local disk. So it's kind of doubly inefficient that way. You're reading it from S3 only to persist most of it to disk and then unpersist it again when you need it. So the better solution is to stream it from S3 so it will do the shuffle at the same time it's streaming in from S3.
So if I use the data frame and you use it later, is that what we do? Because it is not going to do with anything until like reset anything.
Can you repeat the question?
So this is raised if I actually read the content into the data frame, we're not doing until I actually use the data frame later.
By default, yes.
So that is an example of me doing this.
Yes.
Okay.
So this Parquet method that we've created, the save method, it calls the count method. And because it calls the count method is what's called an action in Spark. An action forces Spark to actually execute the code. And so since the count method is an action, it will take whatever data frame it's doing the count on and force that entire pipeline to execute. In the case of the parquet, the only part of the pipeline it's actually executing is reading in the rows from S3. And then it persists those in memory for you to use later. The reason I do it this way in class is because I don't want every query I run to take 5 minutes while it loads from S3. Yeah. Yeah.
Okay, this is my question about the redirect table. So I have a page, and this is just an example. I have a page in my page file with this ID. It says it is redirected. I don't know how true that Boolean flag is. Okay, but in the redirect table, I actually have a record that says it redirects to this.
Okay.
When I then take this back to the page table, I have a record that also says it is a redirect, which then has 3 records in my redirect table. One that's this, one that's this, and one that is itself. This is the cyclic one chain. Okay, these both have records in the page table, and they both say they are in states that the flag that Boolean is redirected is false. So I don't know. Okay, so if I don't know what the ideal is or what I'm supposed to be doing here. So when I see this, I'm like, oh crud, I can't just do a join to deal with redirects. Because a join would only get me this, and that's not my end state redirect page.
Well, see, that's part of the judgment you have to use when you're cleaning data is how far you want to take it, right? Because this state doesn't really apply to that many things in the Wikipedia table. So what I would do, or what I did, is I took everything that is a redirect, or if it's the target of the redirect and it itself is a redirect, I just delete it. I was like, forget it. We're not going to deal with this crap. I'm not dealing with redirects as redirects. This is stupid. I don't want to deal with it.
Okay.
Because Wikipedia should organize its links so that redirects are at least flattened into having one layer. But if they're not, like, I want to deal with this crap.
Okay, so
there are like 40 rows out of 60 million in here.
Okay,
it's
so
not that important.
if I have another ID1 and this comes through as my ID2, okay, and let's say they point to each other. And this is a redirect that points to this, that points to this, and this points to this.
So wait, this redirects to 3 different pages?
Yes, it does. Okay, so what is the right, what do we want to have happen? What should be here?
I would legit just drop it. Just don't even include the redirects set.
Okay.
So your result set doesn't have to be the exact same as mine. It just has to be reasonable.
Okay.
That's right. I just dropped it. So you can do the same thing. You can do the redirect closure if you want.
Well, I actually wrote something recursive to your, but it's not happening.
It's not happening.
No, it doesn't like it. So
Spark doesn't like recursion?
No, it doesn't.
Imagine that.
Okay.
We have something in common. But yeah, this is a perfect example of real world data sets just being atrocious garbage. Like, what is this? What is this page, according to the table, redirecting to 3 other pages?
And one of them is itself.
And one of them is itself.
So just still doesn't smell a leak yet.
No, it's not. Like, it shouldn't have this.
Second page, which the Boolean flag says is also redirected. So then when I go to look for what it redirects to, it redirects completely.
We can I actually want to take a look at this because this is a perfect example of terrible data quality and how to deal with it. Okay. Hmm? Yeah, I seriously doubt Wikipedia is doing any proper tracing on its redirects. But that's what's so confusing. It's like, why doesn't Wikipedia have some kind of constraint in its database that basically says you cannot redirect to a redirect? And if a page is the target of a redirect, you can't redirect it to another page until you redirect all the other links. Like those are fairly simple rules that you could probably do with a transaction, with a SQL transaction, because that's what Wikipedia's data source is. Oh, we're getting it.
Okay, so your logic is that if you get these pairs and one of them redirects to something that indicates it's also redirected, you just exclude the whole thing. You say
Yeah.
it's dirty data.
Yeah, this is dirty data. I'm not going to deal with it. Go away.
Trusting that redirecting by in the page table.
I mean, you don't even necessarily have to because we know that the redirect Boolean flag and the fact that this exists in the redirect table are like two different things. And so you can use either one that you want.
Okay.
Or a combination of the two or whatever. Or you could still include this garbage in your data set if you wanted to. And it probably wouldn't affect anything besides the garbage. So it would basically say, what would it say? Like if two things redirect to each other and you just did a simple join to replace them, they would just swap IDs and nothing would change besides that.
Right, but once you redirect this, you're now going to get three rows, because it redirects to three servers. So what I'm trying to do originally is get my two pairs over this to the left, this is some on the left, and I'm trying to replace that number under ID, right, with whatever it actually redirects to. And so the question is, like, assuming you can have multiple layers of redirects, it's done, but let's just say you can. I wouldn't even know which of those top two that it redirects to is the right one.
You're saying in the redirect table, there are three redirect targets for this ID?
Yes.
I want to check that because I was pretty sure that it was a primary key, but yeah.
No, not in the redirect table. The redirect table redirects it back to a page, but then, oh yeah, that then redirects.
So then you're saying there are three entries in the redirect table where redirect from is this out.
You know what? Yes.
Let's check because that is quite problematic if that's true.
It just has a, this is probably it. It's probably one, but it goes back because it links that to page with the title, and its title links that to three pages with the same title. There's three different items. I think that's the deal.
Three pages with the same title? Oh.
Yes, I think that's the problem.
Did you join on namespace?
No.
Yeah, that might be the problem. So if you don't put namespace as your join key, you might have multiple pages with the same title, but in different namespaces. Like one page is the article page and the other page is the talk page and such and such. That might be the source of this problem.
Okay.
Because this should be a primary key. Let's check. Um Nope. Okay, greedy overview. That's what it's called. Yeah, redirect from has to be a primary key. So something is,
The name of the, yeah, it's the title that's going back, so.
yeah, something is deeply wrong in my SQL if you have multiple rows for this primary key.
Yeah, no, it's because of the title.
Yeah,
I just
okay.
need, like you're saying, if I do it with title and namespace.
You also need to join on the namespace. Okay, I'm glad we got that figured out because that was scary. Any other questions?
Okay, so those probably, if, so those top two probably, they have the same title, but different namespaces. And we just don't know why it's also then going back to itself.
No. Is it going back to itself? That is also something interesting to check. What am I doing wrong? Whoa. Whoa. Table or view redirect cannot be found. Did I not load them all in? Oh, I see. I see what I did wrong. I didn't use my alias. According to this thing, is this the right ID? Is that a 0 or an 8 by the 6? Is that an 8? The 1951 Cal Poly Mustangs football team. I love the kind of stuff that appears in this data set. All right. Does anyone else have a specific question on the data? That was interesting.
I'm, I'm kind of imagining during the. So like, are you looking at this card code and then, because to double check, I would name a check and code is to do that. After you, but I assume you're not going to go through all of the output tables and you also do that.
Oh, I can. I can check your output tables and see how well it matches up with mine. So like I can do a diff between your output table and mine and make sure it's not too much. So it's that combined with reading your code and making sure you're doing all the redirects properly and stuff like that. And if you want to test your code for correctness, you can. Did we talk about like synthetic data sets and such? I may have briefly mentioned it. Yeah, I would strongly recommend creating a small synthetic data set that you can use that will run through all of your code and produce an output that you know is correct because you create the data set, so you know it's good, and make sure it produces the output that you want. So for that small data set, you can extrapolate the correctness for the larger data set. Because for the larger data set, we don't actually know what the correct answer is because we'd have to just go and manually check everything for the large data set. So you can't really do that. So that's how I did it for mine. I can show you the synthetic data set I made just as an example. Flip the solution. Okay, there we go. Okay. So this is my kind of sample for the pages, right? what I did was super simple. I created one page, which is just page one, and that links to a bunch of other pages. And depending on the relationship to the other page, a row in the resulting data set may or may not appear. So I specify like, 18 different things in here, 18 different pages in here, and all of these pages have like a different relationship to page one. So one of them, has a direct mutual link between page one and page two has a direct mutual link for page one. So page one links to page two also links back to page one. So for like page 3 and 4, we have page 4 redirects to page 3, page 1 links to page 4, and page 3 links to page 1. So by extension, there's a mutual link there because 4 redirects to 3. So it's testing those combination of logics. So there's effectively 18 tests in here, and there's, one other page per relationship I want to test. So it's a really small data set, but it gives me what. And this is what, the page, the sample page links table kind of looks like. And I also created a link target sample. So this is the link target for every page in there. And this is the redirect stuff. So, oh yeah, page 3 redirects to page 2, page 5 redirects to page 4, and so on. So create a little sample like this and run your code through it. And if that gives you what you expect, then you can run it on a larger data set with peace of mind. Make sense? Good, good. Any other questions? Okay. We can start talking about shuffles now, more generically. This is sort of related to Trina's earlier question. So more broadly speaking, independent of aggregations or joins or what, yeah.
So because of this exact, I'm sorry.
No, you're fine.
Because I know I have lots of joints, green screen, and putting and like pages, like I have lots of different maps.
Yeah.
Can I force it to use the not hashed-in?
Can you force it to use sort merge join? So sort merge join is basically the default for Spark at this point. You have to try to not make it a sort merge join. Yeah, in general, the sort merge join tends to work better because it's more memory friendly, especially for data sets with lots of unique join keys.
So if I didn't, let's say I didn't have a smaller base and I had like a very big, then I could force it to that.
I mean, we tried that in class. I don't think there's a way to guarantee that Spark is going to use a particular join strategy.
We never did figure out. So we
No.
just need to know. So we are just having to know they are. We were assuming the Spark's figuring out it's going to use.
Yeah, we can trust Spark, which I don't really like to do, but I would love to have more direct control over it. But this is why I've contemplating rewriting Spark in my own image so many times. So many times. I've wanted to do this for a while. All right. So broadly speaking, when we talk about a shuffle, what is a shuffle? Right? Shuffle happens when we need to exchange data between machines in the cluster so that we can compute something. In an aggregation, we need to send everything with the same aggregation key value to the same machine in order to do the aggregation and come up with that aggregation value. For joins, we need to send everything with the join key to the same machine in order to produce those pairs of rows. So for joining, redirect on the page table, we have the stuff about redirect. So we have the information about the ID of the page that is redirected to another page, and we have the title of the redirect target. What we don't have is the ID of the redirect target, so we need to join that with the page table to come up with the ID of the redirect target. And that requires a shuffle. So in both of those cases, a shuffle means we're going to exchange data between machines. There are other sources of a shuffle in Spark, but those are the two main ones you need to worry about. There are two other ones that we're going to talk about briefly, but just thinking about it, can anyone think of a construct in SQL or in Spark, because you've been exploring the documentation a little bit, I've assumed at this point, besides an aggregation and a join that you think would require a shuffle? So which operation seems like in order to complete it, you would need to exchange the data?
For the set, you use them.
Create a set?
Because it's going to, when you start data in sets, or every set, it's been dropped in. So we have to tap all of the this to drop, to drop.
So what do you mean by creating a set?
If I use a construct of a set, but defined as a set, and I add data to it, because of the set as a definition of as a data, right? It's not as
Yeah, a set has no duplicate value. Are you talking about a set in a data frame sense, like the data frame is a set? Or do you mean a set within a row of a data frame?
I remember when we were used set as a data structure in that one aggregation.
Yes.
So if we store data in a set data structure and it manages the properties of a set within that data structure, that data would have to be together in order for it to keep those properties true.
Well, depending on what you're doing, the set wouldn't really require an exchange. Right? So imagine, let's see, I'll give you an example. So Spark has, set-based functions that do not require a shuffle. So good example is, where is it? Array distinct. So array distinct takes the values of an array column and removes the duplicate values and then returns another array. So that sounds like it's taking the array, making a set out of it, and then returning an array. That's a row-wise operation. You can do that on a specific column, and you don't have to exchange the data to make that happen because the set is only being constructed within a specific row.
Oh.
Does it make sense?
For the whole call. Or if you're doing it not row-wise. Like what if I have a list of 1,000 values? And then I put them in a set. And basically what I'm saying is just store the distinct values in sets. In order for it to combine, in order for it to figure out when you're distinct, it has to have them all in place.
Well, like I said, that depends on kind of what level you're doing it on. If you're, trying to aggregate by key and you want a set of all the distinct values for that key, then yes, that would require a shuffle, but that's just another kind of aggregation, right? Like we could write there's an aggregation somewhere in here called, I think it's called collect set. So what collect set does is you can aggregate over a column by key, and then it will store all of the unique values for the aggregated column in an array, and then it will produce an array column of just the unique values. So that's what collect set does. It's very similar to what our count distinct implementation did. So if you look at our kind of custom count distinct implementation, where did it go? It's here. In our count distinct implementation, every time we add a new row, we just maintain a set and we add a new value to the set. And if we add the same value twice, it doesn't really make a difference because it's a set. In the collect set aggregation function, literally the only difference is in the finish method, where instead of returning the length, we just return a list instead. So that would be the only difference between count distinct and collect set, is the finish method. Make sense?
Okay, so you're saying that's really kind of.
So that's really an aggregation.
Sort something, or you're going to do anything required sort, like take a new that won't be that.
Yes. So and that is a very important point. So the SQL construct order by, you can take a data frame and you can order the values in the data frame by whatever combination of columns you want. You almost never want to do this because of how expensive it is. A distributed sort is an intensely expensive operation. You almost never want to do this. And that's because you have to go through these sortings on multiple levels. You have to sort you have to sort all the rows within the partitions, and then you have to coordinate between the partitions to find out, who has the largest value and which partition the largest values are going to go to, and the second largest values, where are those going to go to, and so on. So you have to do all of this coordination and shuffling over and over and over again. That's partially why, for example, training a decision tree in a distributed environment is so inefficient, because training a decision tree requires continuously sorting the data over and over and over again.
So we were to train a decision tree that be better for us to just create the largest instance that we possibly could.
That is exactly what I have suggested to the data science team, which we have not done yet.
If I create a cluster with I'm creating a cluster of one instance in instance.
You can, but Spark's logic still applies. And so Spark will still try and shuffle the data. And it will still try, because every task for Spark only runs on one core in an executor. And so Spark will still follow the same algorithm that it follows, regardless of whether it's actually distributed or not.
If you were to want to run that on one, on other instances, you couldn't do it with Spark.
No. So
itself is going to always.
Yeah, it's basically going to act like it's distributed even though it's not, because the code and the logic don't change just because there's only one machine, right? And my suggestion has been, since our primary omni-score machine learning product at Count is a random forest model, and a random forest is just an ensemble of decision trees, I have suggested that instead of training it in Spark, we just spin up this massive hulking beast of an EC2 instance and let it run for a day or so and train it that way using scikit-learn. No takings so far. But hey, I've done crazier things at Count that have actually worked. And I would love to talk to you all someday about doing big data analytics without Spark. I don't know if you do want to discuss that. That's a much more advanced topic than we are going to discuss in class right now. So if we reach a point in the semester where I don't have anything else I'm interested in talking about where Spark is concerned, then we can just kind of decide what we want to talk about next because it's fun. Sound fun? All right. So sorting is definitely one of them. So sorting, you absolutely want to avoid doing at all costs whenever you can. If something requires a distributed sort, simplest answer is don't do it and find another way. Please. Don't do a distributed sort. Another thing is where you can deliberately induce a shuffle without actually like doing anything with the shuffle is a repartition. So we talked about this a little bit last time, but a repartition will just take the existing partitions within Spark and shuffle them around a little bit. So it'll send, one subset of rows to another machine and it will even them out. So if your partitions are skewed in some way, that can be a way to fix the problem. So like if one partition is larger than the other because this partition was the result of a join, and maybe this particular partition in the join produced a lot of rows and you want to redistribute it again, that's how you can do it, is a repartition. So when you repartition a data frame in Spark, you need to select the number of partitions you want after the shuffle. You can optionally also select a combination of columns to repartition on. So if you select a combination of columns, that means that every row with that combination of columns gets sent to the same partition. So let's say we wanted to take the page links table and we wanted to do something with the page links table. If we wanted to do something with the page links table, we could repartition the page links table, and then we could select like the source ID of the page links table and repartition by that. So that means that every page link that originates from the same page, that gets sent to the same partition. And so that's why repartition is very useful in combination with sort within partitions. Which will take every partition without shuffling and sort it by the column that you list out. And so that way, if you wanted to loop through all the rows in the partition and then for every key do something with it, you can, and you can make sure using sort within partitions that all of them are together. So when you're done iterating through that particular key, you can kind of forget about it and move on to the next key, and you don't have to keep track of everything. That's good.
Is this, regardless of whether I actually have a story on that? Is this true of even new reading and then? So like when you're reading on our tables, I have 4 tables into this project. Could I make them to enforce the partitions based on things I know I want to join on?
You could.
And then I know that
You could, but there's no guarantee that Spark won't shuffle it again anyway. So you might just be wasting the time. I remember trying that before a while ago and having it not work. But you are welcome to try. That was several Spark versions ago. Maybe it's gotten better. All right. So you can repartition, and that's a shuffle. You can sort, and that's a shuffle. Something else, which is a shuffle, that doesn't normally get talked about as a shuffle is distinct, the distinct operator. So let's say we have page. We have the page table. So if we wanted to reference the page table, and let's say we just wanted the titles of all the pages. And we know from the conversation we had about 15 minutes ago that a title is not necessarily unique. So it might be repeated in this page data set. So if we only want a list of the titles, how can we stop the titles from repeating? Well, in SQL, that's just select distinct, right? You can do the same thing in Spark. So we can do page table dot. So if I did page dot select page title dot distinct, and let's just say I want to know just how many distinct pages there are, distinct page titles there are. I don't necessarily care what they are. I just want to know the amount. So that might take a minute or so. And this output requires a shuffle. So if we look at the Spark UI, oh, looks like it returned. Whatever this number is. Oh, that's surprising. So there are 46 million unique, but there are 61 million rows. So that means, 15 million of these rows have a non-unique title, which is interesting. All right. So we can see right here that it's doing a hash aggregate right now. And so we can kind of see the hash aggregate going in two stages, because what this distinct is doing is this is exactly like the collect set aggregation method, except it works on the entire data frame as a whole. So what the hash aggregate does is it will basically collect all of the values for this page title in a giant set per partition. And then once it finds all the unique values within each partition, it will take all of the page titles and then exchange them, making sure every row with the same page title goes to the same machine. And if it finds duplicates, then it eliminates them in the same way that that any other set operation does. So the distinct is exactly like a set operation. Now, what if we tried to implement this a different way? I want to actually see whether Spark will optimize this out or not. You want to make bets? Let's see. So let's do it without the select. Let's aggregate. And let's just do a count distinct of the page title. Now, I want to see if this takes an absurdly long time or if Spark will optimize this out. I am betting that it won't because I have no faith in Spark, but I hope it surprises me. Oh, look at that. It did. How wonderful. Okay. So here's what I was expecting to happen. What I was expecting Spark to do, stupidly, is to not optimize this at all. And because we're doing like a normal aggregation, what I was expecting it to do is create a count distinct aggregation instance within itself, add a bunch of stuff to that. And because we have so many unique elements, what it would do instead is it would take all of those sets and send all of the sets to the same machine because we only want one resultant row. That's what I was expecting it to do, but it didn't do that, and I'm very happy. Because what would have happened if it had done the stupid implementation? It would have put all of the possible values into the same set and then sent every single set to the same machine, which completely defeats the purpose of using the distributed system. So one machine would be receiving all of these unique rows. That's what I was expecting to happen. And it probably has an optimization in there somewhere. Like if it's aggregating by key, then it'll do this count distinct issue. If it's not aggregating by key, then it'll do it the efficient way. What if we wanted to do something evil?
Okay, so the efficient way is that it combines the states with a lot of time on any of the genes, but and then doing sending also and you can do, you still have to combine, you can't figure out your count, and it's not very, you have to compare your lists of distinct counts, right?
Well, sort of.
All of these sets up on the sheet, you compare two sets here and two sets here and two sets here, and it's then is your last thing can you just sending the last two sets, right?
Well, that's not how it works in this example. So in the top example, let's just say the count isn't even there. This distinct will execute all by itself and it'll create another data frame. But this still requires a shuffle. So what it will do is it will send every row, to the machine that it needs to be sent to. And if the machine that's receiving, all of these rows receives a duplicate row, it'll just discard it. So this distinct method to create a new data frame of only distinct rows requires a shuffle, right? But this one over here is doing things in a different way, or theoretically, at least, it's doing things in a different way. So what if we could force Spark to do something stupid? I kind of want to. So what if we grouped by the namespace? Now, the reason why this might boom, I want to see if it does, is there aren't very many namespaces, right? There's maybe a few dozen. And my hope is that Spark will create an aggregation state for every namespace and then try to add a bunch of stuff into the same aggregation state and then shuffle the aggregation states and shuffle them in the same way that we talked about last time, where it'll send all of these unique title values within the namespace to the same machine and break it. So this is where I'm actually trying to break Spark. I'm being mean to it, but I don't feel bad about it. So if we group by namespace, I'm thinking that this might trick Spark into aggregating by key in the way that it normally does. So let's see if that happens.
So the response to me what you said, how we send all of them to the room to
Mm-hmm.
the fact that it's not been doing that. So it's combining seemingly it's aggregation states before and then on the final machine it's only sending to is that what you saying?
Well, the key difference here is that distinct doesn't use aggregation states at all. It's a specially implemented method in Spark that the entire partition, when it receives rows, will deduplicate them.
As it's streaming in.
As it's streaming in. So this happens in two phases, right? This happens before the shuffle. Every partition goes through itself and will eliminate duplicates before the shuffle. And then it will, shuffle the rows in the same way every other shuffle works. And then post-shuffle, when the partitions are receiving rows, they will keep a running tally of the rows they've already seen. And if they've already seen a row, they discard it.
Okay. So let's say you have 6 different instances. And you have lists you have data and everything. So let's say you have so all 6 of them and go through and duplicate their own data. Partitions, that's 6 partitions. So then will all 6 partitions start streaming their data to one other partition or will not? One partition was split into one, one partition was split into one, so you got from 6 to 3, and then from 3 to.
It's
2.
it's not circular. It's exactly the same as every other shuffle works. So here's how the distinct works, right? We have, you know, let's go with color again. We have green on this machine, and then we have another instance of green on this machine, and then we have blue on this machine. And over here, we have green living here. And that's it. And then over here, we have green again, and that's it. So this is what happens before the shuffle. Each partition will go through its rows and eliminate duplicates. So we see green, and then we go and look at it again. We've already seen green, so we take it out. We don't do anything after that. So this is what these two are what gets shuffled. This doesn't get shuffled. It was already eliminated. And every partition will do this. So this only has, this only has one row, so whatever. This thing also goes through its rows. It sees green and it, will emit it into the shuffle. And then if it sees green again, and since it's already seen it and it's keeping stock of it, it doesn't emit it into the shuffle and eliminates it. So now we have 3 greens in the cluster, 3 shuffle. So then we have the shuffle. We need to send this data to somewhere. So blue gets sent to here. And let's say the greens all get sent to this guy up here. Right? So this guy receives now 2 other green values. Now, and since it already has a green value, because it might say, oh, I'm shuffling this to myself because I'm the designated receiver of this key, so I'm just not going to shuffle it at all. So this guy already has the green value. So when he sees another green value, it's going to eliminate it when the shuffle comes in, and sees another green value, it's going to also eliminate that when the shuffle comes in. So after all is said and done, blue gets sent to here. This thing didn't initially have blue, and it saw blue for the first time. And now it keeps it in the set. It saw blue once, and that's all. So at the end of the day, after the distinct, we only have 2 rows. We have green and we have blue. So the shuffle in a distinct works exactly the same way as every other shuffle, except it doesn't really have aggregation states or anything like that.
That's not how it's made.
I was extra mean to Spark. Would it be even meaner to Spark? Yeah, let's be extra mean to Spark. Because apparently this table actually has an amount of memory that can hold this number of distinct page titles for the namespace 0. And that's great for Spark, but what if we wanted to do this on the page links table? So what if we wanted to take the number of unique values in a namespace for the page links table and not the page table? I want to break it. I keep trying to break it. Spark is proving what just happened? Spark is proving too resilient for me right now. And this will take a few minutes. I want to break this in again. All right. So what I want is I want a distinct combination of page link from and page link target per namespace. That's what I want. I want it to have to hold as many unique values in memory as humanly possible in an effort to break it. So, does anyone know what the page link target ID is column in the page links table? I forgot the name. Huh? Uh, so in the page links table, you have PL underscore from, and that's the ID of the source page. What's the column that refers to the link target? Does anyone know the name of it? Okay, that sounds right. All right. This is really me, and I'm not sure why I'm doing this to Spark, but let's try it out. I want to break it. Because a lot of these things will not be computable if the aggregation states are too large. Wow, this is taking its sweet time. Let's see what it's up to. Okay, it's almost done. Everybody doing okay on the project? Yay. It's fun, right? I had fun with it. We've never assigned this project before.
Fun.
Yeah.
Fun, actually. Yeah.
We've never assigned the project before in this class. No.
Fun has been like a also to get the experience.
Well, it has to be due at some point. It has to be due at some point. But I'm glad that most people have started the project at this point. I'm glad you're listening to me because I probably wouldn't have when I was a student. All right, we got this thing loaded in. All right, we've got 1.6 billion rows, and hopefully that's too much for this thing to handle. So let's see what we got here. Oh wow, it already failed. You're not supposed to you're not supposed to die that quickly. Oh, I see what happened. Is it not PL from? It's PL from. Oh, yeah. Now what? What do you want from me? Page namespace cannot be resolved. Oh, it's PL from namespace. Okay. Now let's see if this properly breaks. I'm going to be disappointed if it doesn't. Oh, we haven't finished the jobs. That's promising. Ooh. Okay. Here we go. All right, it looks like that might break. Mission accomplished. Okay. So we can kind of extrapolate from this that the aggregation states from this thing are going to be quite large, right? Because the aggregation state is going to contain every combination of the page link source and the page link target. And it's just going to keep building on the aggregation state. And because of that, there aren't very many aggregation states in here, right? I don't know how many namespaces there are. There are only like 20 in this data set or something like that. So it's only going to produce like 20 rows as output, but all of those rows require so much data to compute that we might not even get there ever. The cluster might not have enough memory to store all that stuff. So what's the solution? What do we do about this? Because in order to count distinct, we kind of have to store everything in a set. That's the only real way to do it. There's no other way to count the distinct values in a set. Unless we can approximate. We're not going to go into the details of how this algorithm works because I don't really know how it works. But there is an algorithm for a prox count distinct called hyperloglog. Hyperloglog is an algorithm invented at Google in like 2014 because they were trying to count the distinct values of incredibly large data sets. And you can't just store the entire set. It won't work. And so what they did was they found a clever way of using hash values and combining different hash values together to form an approximation of how many unique values you would have had to add together in order to produce that hash, which I think is really cool. But like I said, I don't know the details of how hyperloglog works. Maybe that can be what we talk about next time. Because there's other algorithms like that too, which trade off the amount of space it uses for an approximation or lower accuracy. So hyperloglog does that with count distinct. There's another algorithm called count sketch that will do exactly the same thing for the mode. So if you want to calculate the mode of a data set, what you'd have to do is you have to look through every value in that data set. And then once you look through every value, you have to look at which one is the most frequent and then return which one is the most frequent. And so in order to do that, you have to store every value and the frequency of every value. So we have the same problem with mode as we do with counts. And I realize that we're over time right now. Did we actually finish any of these? Oh, we did finish some of them. That's nice. Will it ever finish? I don't know. I guess I'll leave this running during office hours and see what we come up with. Is there anything else that you want to bring up before I stop the recording? Something you want to state for the record? All right. Bye.